Today, we are very happy to have Mr. Claudio Andrea Manzari from Universität Zürich telling us about from heavy to light Z prime solutions to B2S L plus L minus data. Please.
Okay, so hello everybody. I'm Claudio Andrea Manzari from the University of Zurich. First of all, thanks to the organizer for this very nice invitation, and it's a pleasure for me to be here. And today I would like to discuss with you about the solutions to B2SLL data in terms of Z prime models, and in particular Z prime models with a heavy Z prime and models with a light one. It's well known that these models are prime candidates to solve the anomalies in rare neutral B-meson decays. In here, I don't want to discuss their generalities, but I would really like to focus on two interesting features on which I recently worked with my colleagues. So before moving to Z prime models, let me start reminding you about the main motivations for these models, in particular in light of current available data. And I will start from neutral current B decays. So in this context, there are several observables characterized by the underlying process B to S L plus L minus, which exhibit deviations from standard model predictions. In particular, these observables are mediated by flavor changing neutral currents, and therefore within the standard model, they are strongly suppressed, such that they have a high sensitivity to potential nucleus contributions. Here, for example, you can see two of the diagrams appearing in the standard model at the loop level. In particular, these observables are the perfect environment to look for lepton flavor universality violations, since we have a pair of leptons in the final state. And for this reason, we have had in the recent years a huge experimental efforts from several collaborations such as Babar, LHCb, and Bell, which studied the process B to S mu plus mu minus and compared it with the process B to S E plus E minus. And in fact, some of the most interesting observable at the moment are the so-called R ratios, which are defined as the ratio between the Q-squared differential distribution for the branching ratio of a B-meson decaying into a generic A-meson and a pair of muons, compared with the same process with the pair of electrons. Now, taking these ratios, several theoretical uncertainties cancel, such that the prediction within the standard model is very, very clean, and these observables are predicted to be one with a very good accuracy. You can see the experimental situation for some of these ratios in the plot at the bottom of this slide, where you have the measurement from some collaborations and measurements in different Q-squared bins. Focusing only on the LHCb measurements, which are the one in red and the ones with the small x experimental error, I think it is fair to say that a coherent pattern of deviations from the standard model stands out. In addition to these observables, there are then other observables which are theoretically very clean but chirality suppressed, for example, B sub S to mu plus mu minus, and even more observables which are known as angular observables, which are theoretically less clean, but still are coherent with this picture and support the idea of a violation of lepton flavor universality. It is clear that so we have many observables, we have a huge set of data, and to properly assess the presence or the absence of new physics in these measurements, we need to perform a global fit to data. And this is usually done within the model-independent approach of effective field theories. So one defines the effective Hamiltonian as you can see here, integrating out all heavy degrees of freedom up to the mass of the B meson within this Wilson coefficient Ci, leaving only the long distance physics described by the operator OI. And here you can see a full basis of forthcoming operators with a B, an S core, and a pair of leptons. Now, here I highlighted the two operators which are the most relevant for the explanation of this flavor data, and will be useful in the following. Now, let me note, and this will be important for the last part of the talk, that the same approach can also be used for models to study models with the light Z prime, where of course now one is not working anymore in a proper effective field theory, and in fact the Wilson coefficient keep the Q² dependence, where Q is the form momentum of the Z prime. Anyway, this is just to introduce you on how these studies are performed. Let me also give you some detail on the main results that have been obtained so far. The theory community mainly worked in two directions. The first one is to, first of all, understand if data requires or not some new physics contribution. And recently, a group here in Zurich, being very conservative and taking into account the look elsewhere effect, was able to estimate, performing a global fit to all data, that data prefers the new physics hypothesis over the standard model one at the 4.3 sigma level, which means that we are still below the 5 sigma level conventionally considered for a discovery, but we are quite close to it. Then, after this, we are interested in detecting the new physics direction, which is preferred by data. Here we have had many different theory groups working on this, and except for small numerical differences in their results, the main take is that data seem to require a new physics contribution in the muon channel, and additional flavor universal contribution in the muon and the electron channel can further improve the agreement with data. In terms of new physics scenario, which give the best agreement between theoretical prediction and experimental measurements, we have, let's say, all scenarios between the limit cases C9 only in the muon sector and C9 equals minus C10. Here in the plot on the right, I would like to show you just a representative fit performed by Altmanhofer and Stangl, where you have the contribution to C9 and C10 only in the muon channel, so lepton flavor universality violating contributions, and you can see that the best fit point prefers, excludes, let's say, standard model hypothesis by many sigmas. Here, standard model is shown by the 0 point. Okay, so next to this, another interesting sector, at least in light of the recent progresses that have been made on the experimental side, is the Electroweak Fit. And with this, I mean the Electroweak precision observables measured with very high precision at LEP and Tevatron, and more recently at LHC. Within the standard model, the Electroweak sector can be completely parameterized by 3 parameters, which in the following are chosen to be the fine structure constant, the mass of the Z boson, and the Fermi constant. And I'm just giving you these details because, as you will see in the following, we need to take all these observable into account when we study Z prime models. And then, in order to account for higher order corrections, one has to include further parameters such as the hadronic running of the fine structure constant, alpha strong, the mass of the Higgs boson, and the mass of the top. In general, here you can see the conventional set of observables, including the Electroweak Fit, which is the set of observable again with the smallest experimental error. And overall, till the beginning of this year, the Electroweak Fit showed a very good agreement between theoretical prediction and experimental measurements. There were already a couple of tensions, in particular in MW, there was an order 2 sigma tension, as well as in AE and the forward-backward asymmetry of the electron also. But what is most important here to say is that this tension in MW was notably increased by the last determination from the CDF collaboration at the very beginning of this year. And here you can see 2 scenarios, one more conservative and one more aggressive in terms of the estimate of the theoretical and experimental error on the determination of MW, which increased the tension to 3.7 sigma within the conservative scenario and 6.5 within the aggressive one. Last but not least, we have lepton decays, which are, of course, the simplest processes to test lepton flavor universality.
Excuse me?
And
excuse me?
Yes, yes.
Before you
yes.
proceed, could you go to the previous slide, please?
Yes.
So here you show 2 different approaches, aggressive and conservative, and you also have a different prediction for MW, right? For aggressive and conservative. What is the difference for standard model prediction for MW in aggressive and conservative approaches?
Yes. No. So the main difference, the reason for this difference is the error that you consider for the last determination of CDF. Okay, once you because this is an average of several measurements. Okay. So it depends on how you weight the single measurements. Mm-hmm. And if you inflate the error of CDF to take into account the fact that it already shows a quite large tension with respect to the other measurements, then you get a more conservative and then different also value for the mean value of MW.
Mm-hmm. I see. Okay, thank you.
You're welcome. So yeah, I was talking about lepton decays, which are the simplest process to test the lepton flavor universality, and it is straightforward to see how they are modified by Z prime models. In particular, here you can have even 3-level effects from lepton flavor violating coupling of the Z prime. So let's say a Z prime coupling to muon and electron at the same time. And loop level effects from Z prime with flavor conserving couplings. Anyway, if you take the ratios of the processes tau to mu nu nu, mu to nu nu, and tau to nu nu at the amplitude level, in the standard model, these ratios are predicted to be exactly 1, because you are factoring out the different phase space. And if you compare these results with the current experimental averages for these ratios, you can see a smaller than 2 sigma tension, which here I just represented, assuming that we can have new physics only in tau to mu nu nu and tau to e nu nu, which is a reasonable assumption since mu to e nu nu is measured with a much higher precision than the other 2 processes. Anyway, either you consider this as a new hint of new physics, either you just take this measurement as a bound for your model building. These data have to be taken into account to proper analyze any Z prime model which modify them. Okay, so we have seen more or less all the data that we have to take into account, at least the most important ones. So let me start discussing a feature of heavy Z prime models. The following slides are based on work that I've recently done with my colleague Marcel, Andreas, and Joachim, where we focused on the importance of the mixing angle between the heavy Z prime and the standard model Z. So just summarizing what we have said in terms of B2SLL data for Z prime, we know that simple patterns where new physics coupled solely to muons can explain the discrepancies between the standard model and the experiments very well. So we need a lepton flavor universality violating effect in the muon channel, and additional flavor universal effects can further improve the agreement with data. Many models have been proposed in the literature so far, and one of these is known to be Z prime models. Why? Well, this is easy to see because already a three-level exchange of a Z prime can give us flavor universality violating as well as flavor universal effects in B2SLL. And in addition, the mixing of the Z with the Z prime can give a flavor universal effect because the Z prime will induce a Z coupling to BS, and then the Z will couple in a flavor universal way to muons and the leptons. Now, these are the effects in B2SLL, and it is immediately clear that this will have also an impact on the electroweak fit. And the main reason is the fact that we are modifying the coupling of the Z also to muons, to electrons, to taus, and so on. In addition, as we will soon see, a modification of the mixing between the Z and Z prime will also induce a modification of the predicted W mass. So let's start by writing the most general Lagrangian for a Z prime model. And you can immediately understand why there are a plethora of models proposed in the literature in terms of Z prime fields. The reason is that you can couple the Z prime to any fermionic field with almost an independent coupling. Anyway, we want to simplify it, and in particular, we want to simplify it just taking the ingredients which allow to explain B2SLL data. Therefore, what we consider is the last line of this slide, where our Z prime couples to B and S quarks, and in particular has only a left-handed coupling to B and S quarks. And the reason for this is that we know data need a left-handed coupling to quarks. And then we also keep a vectorial coupling to leptons. At the moment, we leave this coupling very generic. And again, vectorial because we know that we need the vectorial coupling to muons to explain, at best, B2SLL data. Then, next to this, we have the kinetic terms for our Z prime, and here you can see the last term giving the mixing between the Z and the Z prime. Of course, here what we are assuming is that the breaking of the electroweak symmetry and of the new symmetry giving rise to the Z prime are related. This is quite a natural assumption, even though it's not necessary. And this is the reason why you can find several models in the literature with the Z prime explaining B2SLL data where this mixing angle is somehow suppressed by different means. Anyway, in our case, what we have to do is to diagonalize this mass matrix between the Z and the Z prime. And as a result, we find two mass eigenstates, which here are denoted as Z and Z prime without the zero subscript, which are just a linear combination of the interaction eigenstates. And this linear combination is given by this mixing angle psi, whose sign is reported here in this red square. And here we assumed, we expanded in VEV over MZ prime. So we assume that MZ prime is larger than MZ. Here, in particular in red, this will be important for the following. You can see how the mass of the Z eigenstate is modified with respect to the standard model one in terms of the mixing angle and the mass of the Z prime field. Okay. So we are ready now, we have all the ingredients to start looking at data. And first of all, since we have a Z prime coupling to leptons, we include electroweak precision observables, data from neutrino trident production, bounds on forthcoming operators obtained by lepton, BS mixing, since we have a coupling to a P and an S quark, and then data on lepton decays. Now, performing a global fit to all this data, you can see on the left of the slide the result that we get for Z prime with a 1 TeV mass in terms of the coupling to first, second, and third lepton generation. As a result, you can see that the coupling to first lepton generation are much stronger constrained with respect to second and third generation. And this is mainly a result on the data from E+ into E+- processes from Lep2. And additionally, you can see that data seem to prefer an anti-correlation between coupling to second and third lepton generation. So that it seems that all these data together point toward a sort of L mu minus L tau symmetry, where the coupling to third generation are very suppressed, and in the following we really take them to be 0. And then we have only one parameter, G prime, such that the coupling to the second generation is G prime, and the one to the third lepton generation is minus G prime. So we are left with three parameters: the coupling G prime, the mass of the Z prime, and the mixing angle. Now, I'm taking this L mu minus L tau symmetry as a concrete example in the following, but the result don't change completely if you take, for example, a B3 minus L2 symmetry or other examples. So we look at the B2SLL. Here, as we said in the introduction, we have a lepton flavor violating effect in C9, and this is proportional to the coupling to muon, and a flavor universal now effect in C10 and C9, which is proportional to the mixing angle. So we look at the two data together, and here you can see a nice complementarity between the regions preferred by B2SLL data in blue and the regions preferred by Electroweak plus tau to mu and the other observable that I showed you before. Here in particular, you can see the result for a Z prime with a 2 TeV mass and the result in terms of the coupling G prime and the mixing angle. And you see that all data together seem to point to a preference for a non-zero mixing angle. Now, this result include the Electroweak precision observables before the last CDF measurement of MW. So how do we expect this result to change after this measurement? Well, here I reported the prediction for the W mass in terms of the parameters of our model. So you see that is given, I mean, the shift in MW is proportional to the mixing angle squared times the mass of the Z prime boson squared. Let's say that we keep the mass of the Z prime fixed to compare then the two results. It's clear that an increase in MW will lead to an increase also in the mixing angle. And in fact, this is what happens once we include the new MW measurement in the fit. And the reason is that the Electroweak fit at this point becomes completely dominated by this last measurement of MW. And in fact, here you can see that the preference for a larger mixing angle is shown. But then what do we expect for the future? Well, already comparing these two scenarios, you can see that this complementarity is somehow weakened by this new measurement. And the reason is pretty clear. If we look again at B2SLL, you see that, so if we increase the mixing angle, we need a smaller coupling to B and S quarks in order to obtain still the best fit point for C10. But now, if we reduce the coupling to B and S quark, we have to enlarge the coupling to muons in C9 to again obtain the best fit point for C9. And this results in a shift toward the right of this blue region in terms of G prime. So we expect that if we further increase the tension in MW, so if future measurement will determine a larger, even larger value for MW, we are going to lose this complementarity. And the same consequence will also follow from an increase in the tension in B2SLL. Okay, so this was...
excuse me. Yes.
Yes, please.
On the right panel, compared
Yes.
to the left panel, G
Yes.
prime tends to be go to 0 compared to the left panel, right?
Sorry, say again, what tends to be...
So in the left panel, the G
Yes.
prime is from roughly 0 to 2.5 or 3, something like that. Could be large, G prime.
Yes, exactly.
On the right panel,
Yes.
G prime is rather, I mean, near 0, basically, right? Even if you have a larger sign size. So, could you explain why this you prefer smaller G prime in the this post CDF 2022?
Yeah, but sorry, maybe I didn't get the question. So you're looking at the blue or the orange region?
Orange. I'm talking
okay.
about orange.
Yeah.
The orange part,
Okay.
the best fit region is close to 0, right? G prime equal to 0. Include
G prime. Yes.
Yeah. But
yes,
in the left panel,
the region.
Yes.
Yes.
Yeah, go ahead, please.
Okay. Yes. So the main reason here is that okay. So if you look at these two blobs here, these are the regions. So for the regions at larger G prime, these are the regions preferred by tau to mu. Okay, so the data from lepton decays, because the lepton decays do not almost depend on the mixing angle, and they depend only on the G prime coupling, such that they need the larger coupling to explain the small tension that I showed you before. But once we include the MW measurement, the fit is almost dominated by this measurement. So you get a much larger mixing angle. And for this reason, you need a smaller G prime, otherwise you would completely mess up the rest of the electroweak fit. Because the mixing angle affects not only MW, but also, for example, the decay of the Z boson, like the Z into leptons. So you need to keep G prime much smaller in order to not get other large tensions in the electroweak fit. And these overwhelm the preference for a larger G prime from lepton decays data.
Okay, thank you.
Welcome. Okay, so anyway, I will show you a conclusive slide again with this plot. So now let me move to a light Z prime. And here, this is the last part of the talk, and this will be based on a work I have recently done with my colleagues Wolfgang, Andreas, Gianluca, Paul, and Jorge. Here, we wanted to investigate whether models with a light Z prime can provide a solution to B2SLL data once we take into account all other constraints for which we have available data. In particular, we wanted to answer the following question: are these models excluded? And in particular, if we consider the minimal set of ingredients that we need to solve B2SLL data, can we already exclude these models? Because of course, if we can exclude the simplest possible model which explain B2SLL via a light Z prime, then every other model which includes these minimal ingredients will be excluded. So what are the minimal ingredients that we need for this model. We need a coupling, of course, a coupling to B and S quarks and a coupling to muons. In fact, we also need something else, and we can easily see why. Here, I'm just showing you some representative observables for which we want to improve the agreement between theoretical predictions and experiments. They are RK star, and P5 prime, some of the observables where we have the highest tensions. And as you can see from this plot, tensions arise in several Q-squared beams. So what we need is quite a large Z prime, so a Z prime with a large width, in order to affect several Q-squared beams at the same time. In addition, we want the Z prime to be broad in order to hide the Z prime in these Q-square distributions, because otherwise the experimental collaboration would have seen a bump in the Q-square distribution of these observables. Therefore, we need to couple the Z prime to an unspecified, let's say, dark sector in order to achieve the desired width. So here, let's sketch the Lagrangian of our Z prime, of our simplified model. We have a Z prime which couples to muons. Now, I keep a vectorial and axial vector coupling. Then a left-handed coupling to quarks. Again, this is because we know that data require these couplings. And here we parameterize this dark coupling as a vectorial coupling to some fermionic sector. Anyway, we checked that changing these assumptions, that is, for example, assuming a scalar dark sector or an axial vector coupling, doesn't change the result of our work. Then we have to look at P2SLL because we want to explain this data. And of course, we have to take into account the effect that we necessarily have G-2 of the muon, and then bounce from B to K star plus invisible, B sub S mixing, and then proton-proton into mu plus mu minus plus invisible, and E plus E minus into mu plus mu minus plus invisible. And maybe I forgot to say that we take into account a Z prime with the mass smaller than more or less 6 GeV, anyway, below the mass of the B meson. So let's start from B2SLL. Here we have an effect in C9 and an effect in C10, proportional to the vectorial and the axial vector coupling of the Z prime to muons. And in addition, as you can see here, and as I said at the very beginning of this talk, we have to keep the Q-square dependence in the propagator of the Z prime, and also here the dependence on its width. It has already been shown by Sala and Straub that a light Z prime can provide a solution, a nice solution, a good agreement with data for B2SLL for a mass above 2.5 GeV. So we make this assumption also in the following. And now we move to G-2 of the muon. Here you can see the exact result at the m mu squared over mz prime squared order for G-2 of the muon, which depends on the interesting combination vectorial coupling to muon squared minus 5 times the axial vector coupling squared. Now, let's stop here for a moment and look at this result, because the interpretation of the G-2 data, it's quite tricky in this context, because we are not really interested in explaining it. But you also don't want to overshoot it or undershoot it, because it would mean that you need also additional new physics then to explain this data. So we preferred in our work to keep an agnostic position and just assume that our model gives the exact combination which does not give any effect in G-2 of the muon. This has no impact at all on our discussion for B2SLL. And the reason is that we know that for B2SLL data, a good agreement between theory and data and experiment is given by all scenarios between C9 and C9 minus C10, as I told you already. And this gives exactly a scenario in between of the two. Anyway, here you can see what's the picture for G-2. So the blue and green bands are the 2 sigma allowed regions for the G-2 data for different Z prime masses. In red, here you have the assumption that we are taking for GV and GA relation. And you see that in terms of model building, a small deviation from this assumption can also explain G-2. You can fall within the regions allowed by G-2. While here in gray, you have the assumption for GV and GA, which do not give a good fit for B2SLL. Anyway, taking into account the fact that the situation for G-2 is not very clear, also in light of the recent lattice determination, we prefer to keep the agnostic position that I told you before. So, once we have this fixed, we performed a global fit to B2SLL data, keeping this assumption. And what we found is that a Z prime with a weight between 10 and 20% gives a good fit to data. And here you can see the result of the fit as a function of the Z prime mass and the coupling combination which enters in C9 and C10. So the coupling to BS quarks times the coupling to muons. In particular, you can see that there are 2 solutions. A solution around 2.5 GeV and another one at a higher mass between 4 and 4.5 GeV. So the main goal in the following is to look at the bounds on this coupling to see if these regions are allowed or already excluded by current data. And let's start in particular from the coupling to B and S quarks. Here, it turns out that the strongest constraint comes from B to K nu searches. Here, the strongest bounds are have been obtained by Babar and Bell, but we were forced to use the data from Bell 2, which is slightly weaker than the other 2. And the reason is that we are looking at a similar process, which is B to K or K star plus invisible plus dark matter. But our dark matter now can be also massive. And therefore, we need to recast the experimental analysis, taking into account the experimental efficiency as a function of the mass of this object. And only the last Bell 2 analysis provided us with this efficiency function. That's why we need to use this bound. We need to use this bound in our analysis. So we computed this branching ratio, keeping the Bright-Wigner of the Z prime. And in particular, here we found that it was also important to keep into account the S or Q squared dependence of the width of the Z prime. So here you can see all the contribution to our calculation. You have the efficiency function in blue, in yellow, the form factors that we needed to parameterize the decay of a B meson into kaon and Z prime. And then in green, the matrix element squared and the Bright-Wigner squared in purple. And you see, importantly, that the efficiency function is larger for larger S. So you can immediately guess the effect of the dark matter mass here, because the dark matter mass gives you a kinematic limit from which you are allowed to integrate your branching ratio. So a larger dark matter mass will exclude the part where the efficiency function is larger and would, of course, reduce your branching ratio, and therefore your bounds from the B to K nu process. Here, just out of curiosity, you can see the effect of the S dependence in the width of the Z prime for different Z prime masses and for different also dark matter masses. And I just want to show you this plot to show you that for in some condition, you can even have a factor also almost 50% given by the S dependence. Then here, also just for your curiosity, I'm showing you the operator product expansion that we used to parameterize the decay of a B meson into K or K star and the Z prime. And you can note that this two branching ratio depends on different combination of the left-handed and right-handed couplings to quarks. So one could argue that since we are only including at the moment, because we have the efficiency function only for this, the decay of a B meson into a K and the Z prime, one could argue that if we also include the right-handed coupling, we could make this combination such that we remove completely the bounds from this data. However, in the near future, when we'll have also bounds from B to K star, we can constrain independently the left-handed and right-handed coupling. So this won't really impact our result. Anyway, now here you can see the bounds that we could extract from B to K nu on the BS coupling in terms of the Z prime mass and the ratio of the dark matter mass over the Z prime mass. As we already noticed, a large dark matter mass weakens the bounds on the BS coupling. And in particular, at some point at the top right of this plot, we are not able to put any bound on the BS coupling. And this is just because we don't have any experimental sensitivity in this region, due to the fact that the efficiency function really drops to 0 for a Q squared or S order 15 GeV squared. Okay, this will be important soon. Then we look at the other bounds. First of all, we have BS mixing, clearly. So here, for light Z prime masses, one can set up an operator product expansion in MZ prime over MB. But what we found is that these bounds are weaker than the ones from B to K nu, while for an MZ prime which approaches the mass of the B meson, there is no reliable treatment yet. And that's the reason why I won't show any bounds from BS mixing in the following. And then we have bounds from plus C minus into mu plus minus plus invisible, where you can radiate at Z prime in the final state from the muon. So here we have, we used the last analysis from Bell 2. The problem is that, again, Bell 2 did the analysis for a narrow width Z prime, therefore we had to recast their analysis, including a sizable Z prime width. And we took into account data from 276 inverse picobar, but I will show you also the projection for 50 inverse femtobars, and even the projection to 5 inverse attobar, where we just rescaled by the appropriate luminosity factor. And what we find with current data is a bound on the muon coupling of order 10 to the minus 1, 10 to the minus 2. And finally, we have data from Drell-Yan proton-proton into mu plus, mu minus plus invisible. Here, Bishara, Haish, and Monni could put bounds on Z prime models, studying the modification of the Z line shape in this process due to the final state radiation of a Z prime. And here you can see the result that they obtained for vector versus axial coupling for different masses of the light Z prime. Now, taking all these bound together, we can look at the results in two alternative ways. Remember that what matters for B to SLL is the product of the coupling to BS times the coupling to muons. So we can, first of all, maximize the coupling to quarks allowed by B2K mu and look at the bounds on the muon couplings. This is what I do in this slide. Let's start from the worst scenario at the top right. You have that the dark matter here has the maximum allowed value. This weakens at most the bounds from B2K nu. And in fact, you see that we can put bounds on the muon coupling up to less than 4 GeV, because after this, we cannot put any bounds on the BS coupling, and the muon coupling can be as small as you like. So here the main result is that current data in solid lines here cannot probe at all the 2.5 GeV solution for B2SLL. Future projection for E plus E minus into mu plus mu minus can start probing the solution and can almost totally probe it when we reach 5 inverse attobar from Bell 2. Then we have a brighter scenario at the bottom right, bottom left, sorry, when the mass of the dark matter is smaller, and this allows to have stronger bound from B2K nu. And again, you see that current data cannot again probe almost any part of the solution to B2SLL, but future projection can probe the solution at around 2.5 GeV and can also start testing the solution between 4 and 4.5 GeV. Now, let me tell you what's the main difference, the most intriguing difference in terms of B2SLL data between these two solutions. Well, it happens that this low mass solution will predict a value for RK and RK star larger than 1 in IQ squared bins, while this larger mass solution will predict a value for RK and RK star smaller than 1 at IQ squared bins. At present, we don't have data to disentangle between these two solutions, but this will be available in the near future and can also give a consistency test for these models. Now, you may be wondering about the coupling of the Z prime to neutrinos. In fact, so far I didn't mention it at all. So here the point is that we are talking about a light Z prime. Now, a light Z prime can be also realized well below the electroweak symmetry breaking. And this means that we are not forced to take into account the SU2 left symmetry. So in principle, one could think at a model which realizes the Z prime below the electroweak symmetry scale and only couples to muons and not to muon neutrinos. I'm not aware of any model at the moment which can do this, but you can see that this can be achieved via some cancellation, at least at the operator level, because in the conventional SMEFT basis, the coupling to neutrino is proportional to a certain combination of the operator O phi L3 and O phi L1. So maybe this is achievable, but I'm not aware of how to do this. Therefore, here I want to show you what happens if you take into account also coupling to neutrinos. Well, in this case, we have very strong bounds from neutrino trident production data. And here you can see in red the bound that this will set on the vectorial coupling to muons. And as you can see in red here, this would completely exclude any possible solutions in terms of a light Z prime. So this means that if you want to build the models with a light Z prime that can provide a solution to B2SLL data, you need at least to cancel by a couple of order of magnitude the coupling to muon neutrinos. And finally, we can look at the same result before in the alternative approach where we maximize the coupling to muons and look at the bounds on the BS coupling. Now here to show you a more interesting plot for the coupling to muons, I'm already taking into account the projection to 50 inverse femtobar. And here I'm showing you the bounds on the BS coupling from current data on B2K nu and projections where I assumed that this branching ratio reaches the level of 1 times 10 to the minus 5. Of course, I had to assume the same experimental efficiency function, but it's clear that this situation, this picture can be strongly improving on the BEL2 efficiency function. And as far as I know, BEL2 is also working on this. So again, you can see that the low mass solution can already be probed by current data once we have the 15 inverse femtobarn projection for E plus minus to mu plus mu minus. And with further improvement also in B2K nu, we can also start testing this higher mass solution. So let me very briefly summarize what I said so far. I discussed with you about two interesting features of Z prime models. The first one related to heavy Z primes. Here I showed you that the mixing angle, which is often neglected in the discussion of Z prime models in terms of B2SLL data, can also lead to interesting correlation with other measurements, and in particular with the latest measurement of the W mass. And at the moment, we can see a nice correlation between the B2SLL data and the Electroweak data in terms of the mixing angle of Z for a Z prime with the standard model Z. And then we looked at a model with light Z prime, which aimed to solve B2SLL data. Here we discussed the current available constraints from other processes, and we mainly found that current data cannot exclude a light Z prime solution of B2SLL data, at least if we are able to reduce the coupling to muon neutrinos, but future projections for in particular B2K or B2K star plus invisible searches and E plus minus to mu plus mu minus plus invisible can probe for sure the lowest mass solution around 2.5 GeV and start also testing the other solution between 4 and 4.5 GeV. Thank you for your attention.
Okay, thank you very much for the nice talk.
Thanks.
Questions or comments?
Let me just sorry.
I have posed one question about the. First of all, thank you very much for the nice talk.
Thanks.
This light G prime option.
Yes.
Have you also considered the epsilon decay to Z plus mu mu? Epsilon is a BB bound state, so and it can decay to 2 gluon plus G prime because it's it's a charge conjugation -1 state, right? Charge
yes.
Yeah, so it should involve 3 vector bosons, so it can go BB epsilon 1s can go to 2 gluon plus G prime. So and the 2 gluon makes I mean number of hadrons, and G prime can go to mu mu. So
yes, the same.
Your coupling is order of it's a slightly, I mean roughly small, a little bit smaller than alpha electromagnetic coupling, I guess. I think there is an observation of the epsilon 1s decay into glu gamma. So I think
I see.
That's one question.
So concerning this question, no, we didn't look at this. Thanks for the comment. But the main motivation was that so for this you need, if I understand correctly, that the Z prime couples to BB bar, right?
Yeah.
So as I said at the beginning, since we really, so our goal was to exclude these models, to see if this model could be excluded. In the minimal setup, our Z prime coupled only to B and S, so had only a lepton flavor violating quark coupling. because that's the minimal setup that you need to explain B2SLL data. But in a more concrete model,
okay.
of course, you would also have BB coupling and then further bounds. But then once you start including also more couplings, a more structured model, of course, you have many other bounds, for example, from demixing or kaon mixing when you take into account also SU2 invariance and so on.
Maybe the next question may be related with this question too, but you mentioned could you show the slide for the trident?
Yes.
Yes. So here you show neutrino trident. So I think so your statement in the bottom,
Yes.
I'm not sure if I agree with this because
Okay.
anyway, this I mean the easiest way to introduce vector boson is to assume some kind of local gauge symmetry, right? And yeah, not like a rho measure or omega measure in the QCD. So it's more complicated, but anyway, so let's assume G prime is associated with some extra U1 gauge symmetry, new extra U1, and G prime is light. I mean, order of below 10 GeV. And when you compose, when you extend your model to standard model plus extra U1, I guess you still assume this standard model chiral.
You're absolutely right.
Yeah. So in that case,
No, you're absolutely right.
If G prime has a vector coupling to mu, then that means G prime coupled to left-handed muons pair. So maybe have the same size of the neutrino pair coupling to the neutrino pair, right?
Yes.
Yeah.
Yes. No. If you realize your Z prime via an additional U1 symmetry, you cannot avoid. I mean, I don't know any way to avoid the SU2 left invariant. So you must couple also two neutrinos. No. I was thinking, but this statement maybe is not 100% correct, but meant the fact that since your Z prime is light, in principle, you may find alternative ways to generate your Z prime already below the Electroweak symmetry scale. But the U1 extension of the standard model is not such a possibility.
Okay.
Honestly, at the moment, with my collaborators, we tried to think about the way to do it, but we couldn't find one at the moment.
And you discussed in detail, I mean, the case with the light dark matter and the heavy dark matter for the light G prime case. So
yes,
to simplify the situation, what happens if we simply ignore there is no light dark matter? So G prime has no branching ratio into a pair of dark matter. So if the dark matter is just heavy, and then G prime, light G prime cannot decay to dark matter pair and no invisible, so no B2S nu constraint from the B2S nu, etc. In that simple situation, what would be the allowed model parameter space? You probably explained, but just to
so if you assume if you assume that dark matter is so heavy such that you don't have bounds from B to K plus invisible because you don't produce Z prime, then the strongest bounds come from BS mixing. But the situation is even worse in the sense that for let me show you in this plot, for low Z prime masses, the current data and future projection just move upward. So you test even less, and for large masses, you can around 4 GeV, you cannot set any bounds in any case, because there is no reliable treatment for BS mixing in this case, since you are close to a resonance between Z prime and B.
I see. So if so you mean that if we don't include the dark matter, I mean G prime decay into the dark matter, if we do not include that, then in your previous slide, the most constraints, I mean, this light G prime options are still surviving alive, right?
Yeah, honestly, I'm 1 second, let me think, because there is another problem. You need the Z prime decaying into dark matter to explain B to SLL, because you need a large width. Otherwise, I see. Because the problem is that otherwise it is very narrow. And first of all, you could just see it in the Q-square distribution of as a bump, no? In mu mu.
So you know, to have a large, to have a large,
that's a necessary assumption.
Width, you introduce dark matter pair, and then
Sorry. In fact, that's a necessary condition. Otherwise, you cannot explain B to SLL. It cannot be a valid explanation to B to SLL.
Yes. I see. Okay. Now I think I can understand the current status of light G prime solution. Thank you very much. Yeah.
Thanks a lot.
Are there other questions or comments? Okay, otherwise we may thank the speaker again. Thank you.
Thanks a lot again for the invitation.
Bye-bye.
Bye-bye.
Bye.